Yes.
Okay, so I'm Satyajit Ghosh and my mentor is Ankur Bahatia. So our project is single image super resolution and so the introduction. So what is single image super resolution? It is reconstructing a high resolution photorealistic image from its counterpart low resolution image. So this is a difficult task when you have single low resolution image as input has very as we have to recreate a very high resolution image. So what is the motivation for our project? In the literature, super resolution reconstruction is still under development, and there is still a lot of scope for it. The existing methods of super resolution reconstruction do not provide satisfactory results. Also, the high resolution images require higher storage, so it is better to store them in low resolution images. In addition, high resolution images contain more details and information and have less noise. The super resolution can also be obtained from multiple low resolutions. So the important question is to how to increase the resolution. There have been earlier works on this thing too, and these are mainly divided into three categories, which are interpolation based methods, reconstruction based methods, and learning based methods. So what is the problem with the conventional super resolution approaches? The convolutional neural network approaches such as SRCNN, FSRCNN, and VDSR usually use the process of firstly upscaling or upsampling the low resolution image and then perform convolution to get the high resolution image. So since the low resolution image is upsampled at the very beginning, all convolutions will be based on upsampled low resolution image. Thereby, the number of computation is increased. Also, the loss usually used is L2 loss, which fails to capture the underlying multimodal distribution and give a good human visual perception. So the implementation details, we have used LAP-SRN or Laplacian Pyramid Super Resolution Network. In contrast to one-step upsampling, the network progressively reconstructs the subband residuals of high-resolution image at multiple pyramid levels. Without the use of bicubic upsampling, it directly extracts the features from low-resolution input image and thereby low computational loads. It is called Laplacian pyramid because at the feature level extraction, there is one residual image outputted at each level. So there are two branches, which are feature extraction branch and the image reconstruction branch. So the feature extraction branch is mainly has 5 convolutional layers. So these are the features that are being extracted from the low resolution image, which you can see as a butterfly wing. So there are 5 convolutional layers, so which extract the feature. And then we have a transpose convolutional layer, which gives us a better upsampled image. So now we move on to the image reconstruction or the lower one. So these have upsampled from low resolution image by using bilinear kernel. This and the input image is upsampled by a scale of 2 with a transpose convolutional upsampling layer. A transpose convolutional layer on the features extracted from the previous resolution is then combined this plus signal, which is element wise summation, and then the predicted branch is outputted, which is a high resolution image. So this process can be seen here. Features are extracted. So this is only a single feature, which is basically of the order of 64 filters. And this is the transposed feature, transposed convolution on this low resolution image. When these two are added, we get a image like this. So this is the output of the lap SRN on a low resolution image, which is this one. So we can clearly see the furs and all those things are much sharper in this image, in the 4x image. So the loss function used here is Charbonnier loss function, which is much more robust than the L2 loss function. Now, novelty of the project, the LAP-SRN usually has a range of 31 PSNR value for 4x and 27 for 2x. So we have achieved 32 and 28 for 4x and 2x on Celebi dataset, and 23 and 21 for BSDS 300. Also the Celebi dataset, which is basically a a dataset based on faces, has also generalized well for other images too. So future work, we are working on improving the model for general downsampling filter. We are working on fairness or removing bias. Subpixel convolution will be used instead of transpose convolution. Also, we'll later on try the pulse, which is self-supervised photo upsampling via latent space exploration of generative models, which will be tried later on. So we also have a working model. So I'll show that. Uh, yeah. So it takes a little bit of time. Okay, I'll just reload it. Just a second. So since it's running on a free server, it usually takes a little bit of time.
I am just adding a bit as we have done implemented in the project. Actually, in the data set, what we have is we have the high resolution images. So we have to actually do a down sampling to the image so that we can then perform our network to convert it again into high resolution. So the problems which are we are currently facing is that we are having a down sampling. Actually, we are explicitly applying a down sampling to the high resolution image for training. So what happens is the down sampling is performed by a certain algorithm. So if for a general image, if we do not know what a down sampling filter is, then what happens is that the algorithm fails. So this is basically a hot topic in current scenario of research, and many researchers have been present regarding this in this year's CVPR 2020. So I'll just show you image after Satyajit shows the demo to exactly see what the results are.
Yeah, so it's working now. So this is the output image from this one. So you can see there is a little bit of sharpness in the furs and all.
Yeah, so we can see that the first high resolution image at the top is actually upsampled, is actually upsampled from a filter, and the down one image is actually produced from the model. So Satyajit, just end your screen sharing. I want to share a photo.
Yeah.
Yeah. So you all can see in this photo, this is on the left, it is my image, and it is down sampled in the second image. And you can see the reconstructed high resolution image on the right. So the resolution of the reconstructed image is actually very pretty good in the perspective of that we are having a good production of a high resolution, but we can see that generally there is a bias in the data. So this is a hot topic for a research because we are the data which they have used for training the model is actually very biased. That is, it has images of more images of white people than the images of black people. So for example, my color is a little bit blacker in comparison to that of this produced white image. So we can see that the image, the blurred image is produced, the blurred image is changed into a white image. Similarly, we have examples of Obama image from a black people is converted to that of white image. So this is really a very good topic to work on. So we'll be improving our model in the future on this topic. Thank you everyone for seeing our presentation.